This is Lab 3, dealing with the magnetic field of a bar magnet. Here's a table of contents for what will be discussed in the lab. We will start with an introduction. We'll talk about some physics principles used, move into the experimental procedure, look at some of the results, and then check the glow script model we used for the scenario, and then finish with our what if scenario and our conclusion, including any potential sources of error. So to start, the purpose of this lab was to observe the relationship between the measured magnetic field of a bar magnet and the distance away from the magnet, calculating the magnetic field at various positions along and away from the axis. And I used my smartphone setting up a magnetometer app so that the magnetic field was 0 in the x direction, which lines up in the magnetic north. Some goals for this experiment was to find the magnetic field at various points around a magnet, determine the net magnetic field of the magnet, and then simulate the model in GlowScript code that calculates the theoretical magnetic field of the magnet and the space around it. And then we would compare this model to the real-life measurement of the net B at a 45-degree angle. And then a brief insight into results. As the magnetometer on my phone moved closer to the magnet, we saw that the measured x component of the magnetic field increases. Some physics principles used, just Earth's magnetic field. We have to account for the magnetic north, and the experiment was set up along the east-west axis to account for this. And then when the observation point was at a 45-degree angle from the magnet, Earth's magnetic field had to be subtracted from the net. And then there are three equations, as you see here. We have the approximate magnetic field equation, the distance dependence equation, and then the equation for magnetic field at an observation point. The experiment itself was we placed a magnet at the end of a meter stick, used my phone's magnetometer to measure the magnetic field, and then tested the distance to place my phone from the magnet in order to obtain different magnetic fields. And we found the magnetic field at a 45-degree angle from the magnet. And as we stated before, the field increases as the observation location gets closer to the magnet. Interpretation of results, we recorded distances for specific magnitudes in the x direction, moving the magnetometer periodically closer for higher values. And the table shows 3 trials for various Tesla values. And the values in the table are averaged in order to predict even more values, as shown in the graph. And it is easier to visualize by plotting the natural log function that is seen. And then the exponent of the original equation is the slope of the line of best fit, which we saw was negative, and the intercept is negative 21.282. And then using this information, we can calculate the magnetic moment, mu, because the bar magnet is acting as a magnetic dipole, and we can use the on-axis dipole equation we said before to obtain our mu value of 2.86 times 10 to the negative third. Moving into some more results of just the 45-degree angle distance away. We see we recorded the distance where B net was measured to about to be 100 microtesla, and then we moved vertical to the same distance in order to calculate the B net coordinates. And the Y value was corrected by subtracting the Y value due to the Earth's magnetic field in order to get the Y value only due to the magnet. And as shown in the table, we had an average perpendicular distance of 0.169 meters and an average B net of 4.79946 e to the negative 8th Tesla. Here's our GlowScript code here, just going through where the arrows are the changes. The smaller magnitude for the perpendicular magnetic field. And the arrows we see in the final model here. The cylinder is the magnet. The light blue arrows are the 4 perpendicular magnetic field locations. The 2 orange ones are the 2 on axis. And then the magenta is the magnetic field calculated along 45-degree axis. The code itself, we inserted the mu moment here. We created a function for to calculate magnetic field. Then we defined those arrows on the perpendicular and the on-axis locations, and the magnetic field is calculated at each location. And then we used our experimental value of 0.192 in order to determine the hypotenuse and distance d from the magnet to the location, calculating the magnetic field at this location and printing the vector value, which was shown here of 7.14311 e to the negative 9th, 2.14293 e to the negative 8th, 0. And then we saw here that the computer calculated the B net to have a magnitude of 2.2588 e to the negative 8th Tesla, and the experimental measurement is greater than the computer calculations. What if scenario? What if we hadn't oriented our experiment to compensate for the magnetic north? We'd have to count for the different directions of the magnetic field in the dipole bar magnet and the magnetic field of the Earth, thus changing the results, as all magnetometer readings would be skewed in the direction of the magnetic north. And if we stuck 2 identical magnets together, this would just create a bigger bar magnet, thus a bigger magnetic field contribution. As our conclusion, the lab showed how Earth's magnetic field attracts the magnetic field of everything, and more specifically, it showed how the magnitude of the magnetic field increases as the observation location is closer to the magnet. And then potential sources of error was fluctuation of the magnetometer on my phone with my hands, and then adjustments to the actual setup of the magnet on the meter stick, which allowed for potential human error to skew the results.